The last numerical example we want to present today is referred to as the Seiscope Syncline model. This model was kindly introduced to us by Jean Virieux last year and was developed within the Seiscope consortium group in Grenoble. This is an interesting problem as it poses a set of challenges that may be encountered when dealing with complex overburdens, such as salt bodies. We begin by a brief description of the experiment setup and we summarize the main challenges associated with this example. We first show that conventional data space multiscale FWI fails to retrieve a useful solution, and that FWIME is able to retrieve an excellent solution. And furthermore, we closely examine all the different components of the algorithm as we did for the last two numerical examples. The true velocity model is approximately 12 km wide and 3.5 km deep, and it is composed of two horizontal layers with a low velocity synclinal inclusion embedded in the second deepest layer. We generate data with a surface acquisition setting with sources placed every 250 meters and receivers every 50 meters. The maximum recorded offset is 12 km, and the source used contains energy restricted to the 2 to 6 Hz range. Our modeling is conducted with an acoustic isotropic engine, which is also used for the inversion process. The first main challenge is the lack of energy below 2 Hz, and here we're displaying the spectrum of our wavelet used for the modeling. The second main challenge is the fact that the focal point of the synclinal feature is such that it creates a very complex waveform that includes triplications. And we are now going to show you a sequence of slides representing time snapshots of the wave field generated by a shot position at x equals 6.5 kilometers and propagating through the true velocity model. And this will allow us to gain better insight on how complex the recorded data will be. The third main challenge stems from the structure of the initial model. First, it contains an incorrectly positioned high-velocity anomaly since the syncline feature is completely missing. Moreover, this anomaly contains high wave number interfaces with a sharp velocity contrast, somewhat similar to an incorrectly positioned salt body. This is the true model, and this is the initial model, and this is the initial velocity error, the difference between the true and the initial models. The last main challenge comes from the complexity of the recorded data compared to the initial predicted data, thereby creating wrong association of waveforms. Therefore, the observed data are completely cycle skipped, and this indeed leaves no chance to FWI to retrieve a useful solution. This slide shows the observed data on the left panel, the initial predicted data in the middle, and the initial data difference on the right panel. We can clearly see that the initial prediction is completely missing the complex waveform features stemming from the synclinal basin. And as we mentioned, conventional FWI has no chance of succeeding. And this is the final inverted FWI model, and this is the true model. So we apply our FWIME inversion scheme, and we begin by providing details on our parameter selection. Our initial model is the same model as for FWI with the wrongly positioned sharp interface. We simultaneously invert the full data bandwidth, and we conduct our model space multiscale approach using 3 spline grids. For the first spline grid, we use a spatial sampling of 500 meters in both directions. Our horizontal space lag extension ranges from negative 500 meters to plus 500 meters, which is an unusually large span, and this is due to the inaccuracy of the initial model. And now let's examine our initial search direction. The left panel here shows the initial FWIME search direction on the finite difference grid, and the right panel is the true search direction. After mapping onto the first spline grid, we can see that our FWIME search direction is improved and is able to recover the low wave number features from the true search direction. Okay, now we're going to show you the inverted models coming from our model space multiscale inversion. This is the initial model, This is the FWIME inverted model after spline grid 1. This is the FWIME inverted model after spline grid 2. And this is our last FWIME inverted model on spline 3, which coincides with the finite difference grid. And now indeed we can QC our result by looking at the data space. So this slide shows the observed data, predicted data, and data difference at the initial step. This is after spline 1, and this is after spline 2, and this is after spline 3, which is the finite difference grid. And we can see that our inversion was able to perfectly match the observed data, and our data difference has vanished. The last feature I want to examine here are the extended images computed at the initial and final steps. And note here that we're not going to look at the optimal extended perturbation, but simply at extended migrated images. And this is the zero offset cross-section of the extended migration computed with the initial velocity model. This panel shows the analogous zero offset cross-section, but computed at the final step of our FWIME inversion process. We can see a much better match with the true model. And this is the true model. Finally, this slide shows 3 angle domain common image gathers extracted at 4, 5, and 6 km respectively and computed with the initial velocity model. We can see that the velocity model is so inaccurate that the move-outs in these gathers are extremely difficult to interpret. Therefore, we believe that most wave equation-based MVA techniques would struggle to recover an accurate model. This slide shows the same angle domain common image gathers, but this time computed with the final FWIME inverted model. As expected, the events are correctly positioned and display a flat move-out along the extended axis, which indicates that our velocity model is quite accurate. Okay, so this ends our set of videos for this SCP 2020 annual meeting. We hope you enjoyed this last example proposed by the Seiscope consortium. We believe this numerical test is quite interesting as it shows the potential of FWIME at dealing with incoherent gathers, usually resulting from wrongly interpreted complex overburdens.